Imagine this. It is Black Friday. Your API has been humming along at 1,000 requests a second. Suddenly the graph spikes to 100,000. Latency triples. Your database CPU pins at 100%. Real customers see 503 errors. You scroll the logs and find one client, a poorly written script, sending 80,000 requests per second by itself. Every other customer is being starved by one bad actor. And somewhere, a Google or Stripe interviewer is sliding a piece of paper across the table that says, "Design a distributed API rate limiter." This is video 2 of the System Design Problems series. By the end of the next 20 minutes, you will have a complete, FAANG-grade answer that you will actually remember in the room. Before any code, know what interviewers are grading. 5 signals. 1. Do you ask about the dimension? Per user, per IP, per API key, per tenant, or global. 2. Do you pick the right algorithm? Fixed window is wrong for almost everyone. 3. Do you make the limiter distributed? A single in-memory counter on one box does not survive load balancing. 4. Do you handle failure? What if Redis dies? Do you fail open or fail closed? 5. Do you think about observability? How does a customer know they were throttled? How does on-call see who is being noisy? Hit all 5 and you are in the top 5% of candidates. What is a rate limiter, exactly? In one sentence, a rate limiter is a policy enforcement layer that decides whether to allow, delay, or reject each incoming request, based on how many requests the caller has made in a recent time window. The traffic light analogy works perfectly. Think of your API as a busy intersection. Requests are cars. Without traffic lights, every car rushes the junction and nothing moves. The rate limiter is the traffic light. Green means go, your request gets served. Yellow means slow down, back off a little. Red means stop, wait for the next window. A good rate limiter switches these signals fairly, per lane, and never lets one truck block the whole junction. Where do rate limits actually apply? For common dimensions, and a good system has all of them layered. 1. Per IP address. Stops dumb brute force scripts and basic denial of service at the edge. 2. Per API key or per user. The contract level. This is what your billing tier maps to: free, pro, enterprise. 3. Per endpoint. Login is 100 per hour, search is 1,000 per minute, payments is 50 per minute. 4. A global. The total firehose your service can handle without falling over. Every real-world API combines these. GitHub limits per token and per IP and per endpoint. Stripe limits per API key, per object type, and globally per region. Layer them, that is the real answer. Time for the contract. Your rate limiter exposes one function, allow, give it a key like user:245, and it returns one of 3 things. Allowed true, with a remaining count and a reset timestamp. Allowed false, with a retry-after value in seconds. Or, in advanced systems, allowed delayed, meaning queue this request for a few hundred milliseconds and then serve it. On the wire, the limiter writes 4 standard headers: X-rate limit, X-rate limit remaining, X-rate limit reset, and retry-after. These headers are not optional. They are how every well-behaved client backs off cleanly. If you forget the headers in your interview, you lose a full grading band. For algorithms you must know cold. Fixed window, count requests per calendar minute. Cheap and wrong, because at the boundary a client can fire 2 windows worth back to back. Sliding window log, store every request timestamp. Accurate, but memory heavy. Sliding window counter, combine 2 adjacent fixed windows with a weighted average. The pragmatic default. Token bucket, refill n tokens per second up to a max capacity. Each request consumes 1 token. Smooths bursts naturally, and is the algorithm Stripe, AWS, and most CDNs actually use. Leaky bucket, a queue that drains at a constant rate. Good for shaping outbound traffic, less common for inbound APIs. Pick token bucket or sliding window counter as your default, and you will be right 90% of the time. Storage. Where do the counters live? 3 options. In memory on each app server, fastest, but breaks the moment you scale to 2 boxes behind a load balancer, because each box has its own counter. DynamoDB or Postgres, durable but too slow for the millions of increments per second a real limiter needs. Redis, the right answer for 99% of interviews. Sub-millisecond latency, atomic INCR and expire, and Lua scripts that let you run multi-step token bucket logic in one atomic round trip. The pattern is 1 Redis key per dimension, like rate limit :user:245:minute. Set with expire so the key auto-cleans. Read and write in one Lua script so 2 app servers cannot race each other into double counting. Here is the heart of every real implementation, a token bucket as a Redis Lua script. 2 keys as current tokens, and last refill timestamp. Inputs refill rate, bucket capacity, requested tokens. Step 1, read current tokens and last refill from Redis. Step 2, compute how many tokens to add based on time elapsed since last refill, capped at capacity. Step 3, if available tokens are at least 1, subtract, write back, return allowed. Else, write back the updated count, return throttled with seconds until next token. Because this entire block runs as one Lua script inside Redis, it is atomic, 2 app servers cannot both pass the check and both subtract. That single atomicity property is the whole game. Without it, you get a thundering herd that defeats your limit by a factor of n, where n is your fleet size. Synchronization across instances. Why is this hard? Because in a distributed system, the same user can hit different app servers within milliseconds. If each server keeps a local count, the user gets n times their real limit. 3 ways to fix it. 1. Centralize the count in Redis with atomic operations. INCR is atomic by design. Expire makes the window self-cleaning. This is the default. 2. For very hot keys, use Redis cluster sharding so the load spreads across nodes. 3. For extreme scale, use a sliding window counter with eventual reconciliation. Each app server batches local counts and flushes them to a central store every 100 milliseconds. Slightly less precise, but handles 1 million requests per second per node. Almost every interview wants option 1. Mention options 2 and 3 to show depth. The hot key problem. 1 Redis key that takes all the traffic. Imagine 1 viral tenant, every request hashes to the same Redis shard, and now 1 CPU is on fire while the rest of the cluster sits idle. 2 fixes. 1. Hash the key with a salt that spreads it across a small set of buckets. Read the sum at check time. 2. Add a layer of in-process pre-aggregation. Each app server holds a local counter for 10 milliseconds, then sends the delta to Redis. Massively reduces Redis queries per second at the cost of slight burst leakage. Bonus is bake tenant quotas into config. Free tier, 10 requests per second. Pro, 100. Enterprise, 10,000. Read the tier from a cache, multiply the limit, and you have a real multi-tenant rate limiter. Disaster 1. Redis is down. What do you do? 2 philosophies. Fail open, allow all requests, log the bypass, page on call. Choose this when availability is more critical than abuse prevention. Stripe and most public APIs fail open. Fail closed, reject all requests with 503. Choose this for billing or write-heavy paths where uncapped abuse would be catastrophic. The hybrid answer that wins interviews, fall back to a local in-process limiter with a relaxed multiplier, say 5 times the real limit. You preserve some protection while degrading gracefully. Also, circuit break the Redis client itself. If Redis latency P99 crosses 50 milliseconds, trip the breaker and use the local fallback. Recover automatically when Redis health returns. Always page on call. Always emit a metric. Never let the bypass go silent. Disaster 2. Multi-region bypass. A clever attacker notices that your EU West and US East Redis clusters are independent. They send 100 requests per second to each region, they get 200 per second total, double their limit. 3 answers, from cheapest to most correct. 1. Pin a user to a region via consistent hashing at the global load balancer. Cheap, but a single regional outage shifts traffic. 2. Replicate counts globally with a conflict-free replicated data type, or an eventual log. Accurate within a second, but adds cost and complexity. 3. Accept the bypass and tune limits down by the region count. Pragmatic and very common in the wild. The interviewer wants you to name the trade-off explicitly. Mention global replication only if you have the depth to defend it. Otherwise, pin or downtune and move on. Disaster 3. A legitimate big customer sends a sudden burst that they will pay for. You do not want to reject them outright. Token Bucket handles this beautifully. Their bucket capacity is, say, 100 tokens, refilling at 10 per second. Idle for a minute, they have a full 100 to spend in one burst. After that, they are rate limited to the refill rate. When you must reject, never just send 503. Send a 429 too many requests, with 2 headers, retry-after in seconds, and a short JSON body explaining the limit. Bonus, set a reset at wall clock timestamp. Clients can sleep precisely. The best clients implement exponential backoff plus jitter on top of retry-after. The combination of generous burst, precise 429, and clear headers is the difference between angry customers and grateful ones. How real companies actually do this. Nobody runs one rate limiter. They layer 4. 1. The edge. Cloudflare or your CDN drops obvious denial of service before it ever reaches your servers. Hard caps per IP, per autonomous system number. 2. The API gateway. Per API key, per route, per minute. This is where most of your business logic lives. GitHub does this. Stripe does this. 3. The service itself. A finer per tenant limiter close to the database, protecting expensive endpoints like search or report generation. 4. The database connection pool. The last line of defense. If a runaway query gets through, the pool itself caps concurrency. For layers, each catching a different class of abuse. If any one layer fails, the next one still saves you. That is defense in depth, and it is the only architecture senior interviewers actually believe in. Observability is what separates a senior answer from a junior one. 4 things to track. 1. Red metrics. Rate of requests allowed, error rate of requests throttled, and duration of the limit check itself. The check should be under 1 millisecond at P99, or it becomes the bottleneck. 2. Throttle reasons. Tag each 429 with which dimension fired per user, per IP, per endpoint, or global. Without this, your on-call cannot tell a bad actor from a viral feature launch. 3. Top abusers dashboard. A live leaderboard of the top 10 throttled keys in the last minute. This is how you find broken clients and bad scripts in seconds. 4. Alerts on bypass. If failopen kicks in, page immediately. If the throttle rate climbs above 1% of total traffic, page. If a single key consumes more than 10% of a tenant's quota for 10 minutes, alert their account manager. Metrics turn a rate limiter from a black box into a control plane your whole company can use. Now the full picture, in 20 lines of code. Express middleware. Get the user identity from the JWT. Build the Redis key, rate limit, user ID, route. Call the Lua token bucket script with rate equals user tier, capacity equals rate times 2 for burst. If allowed, set the 3x rate limit headers on the response and call next. If throttled, set retry-after, write a 429 JSON body with the dimension that fired, emit a metric tagged with user, route, and reason, and return without calling next. Wrap the whole thing in a try-catch, on Redis error, fall back to the local in-process limiter and log the bypass. 20 lines that handle the happy path, the failure path, the headers, and the metrics. That is your interview deliverable, fully runnable. The 8-point cheat card you will remember forever. 1. Ask the dimension. Per user, IP, key, tenant, or global. 2. Pick token bucket or sliding window counter. Avoid fixed window. 3. Store counters in Redis. Run the algorithm as a Lua script for atomicity. 4. Layer 4 limiters. Edge, gateway, service, database. 5. On Redis failure, fail open or fall back to a local limiter. Never silently bypass. 6. For multi-region, pin per user or accept a small bypass. 7. Always return 429 with Retry-After and X-rate limit headers. 8. Instrument everything. Red metrics, throttle reasons, top abusers dashboard. Memorize these 8, and you will have a complete answer to any rate limiter question, from a startup phone screen to a Google staff interview. One-line takeaway: a rate limiter is the cheapest insurance your API will ever buy. Build it before you need it.